7. SSH Hardening. The Secure Shell Suite is one of those must-have tools for Linux administrators. It allows you to take care of Linux servers from the comfort of your cubicle or even from the comfort of your own home. Either way, it's a lot better than having to don your parka and jump through security hoops to enter a cold server room. The secure in Secure Shell means that everything that you either type or transfer gets encrypted. That eliminates the possibility of someone obtaining sensitive data by plugging a sniffer into your network. By this stage in your Linux career, you should already know how to use the Secure Shell, or SSH, to do remote logins and remote file transfers. What you may not know is that the default configuration of SSH is actually quite insecure. In this chapter, we'll look at how to harden the default configuration in various ways. We'll look at how to use encryption algorithms that are stronger than the default, how to set up passwordless authentication, and how to set up a jail for users of the Secure File Transfer Protocol, SFTP. As a bonus, we'll look at how to scan SSH servers to find vulnerable configurations and how to share a remote directory via Secure Shell File System, SSHFS. In this chapter, we'll cover the following topics: ensuring that SSH Protocol 1 is disabled, creating and managing keys for passwordless logins, disabling root user login, disabling username/password logins, enabling two-factor authentication, configuring Secure Shell with strong encryption algorithms, setting system-wide encryption policies on RHEL 8.9 and all Linux 8.9, configuring more detailed logging, configuring access control with whitelists and TCP wrappers, configuring automatic logouts and security banners, configuring all the miscellaneous security settings, setting up different configurations for different users and groups, setting up different configurations for different hosts, setting up a root environment for SFTP users, sharing a directory with SSHFS, remotely connecting from Windows desktops. So if you're ready, let's get started. Ensuring that SSH Protocol 1 is disabled. In the two previous editions of this book, I told you about how version 1 of the SSH protocol is severely flawed, and how you should always ensure that it's not enabled in the etc SSH config file. Nowadays, you don't have to worry about that, because SSH Protocol 1 is now gone, and is nothing but a thing of the past. So, yeah, it's time to celebrate. Creating emerging keys for passwordless login. The Secure Shell Suite is a great set of tools for communication with remote servers. You can use the SSH component to remotely log in to the command line of a remote machine, and you can use either SCP or SFTP to securely transfer files. The default way to use any of these SSH components is to use the username of a person's normal Linux user account. So, logging into a remote machine from the terminal of my OpenSUSE workstation would look something like this. SSH Donny at 192.168.0.8. Well, it's true that the username and password go across the network in an encrypted format, making it hard for malicious actors to intercept them. It's still not the most secure way of doing business. The problem is that attackers have access to automated tools that can perform brute force password attacks against an SSH server. Botnets, such as the Hail Mary Cloud, perform continuous scans across the internet to find internet-facing servers with SSH enabled. If a botnet finds that the servers allow SSH access via username and password, it will launch a brute force password attack. Sadly, such attacks have been successful quite a few times, especially when server operators allow the root user to log in via SSH. This older article provides more details about the Hail Mary Cloud botnet. In the next section, we'll look at 2 ways to help prevent these types of attacks. Enabling SSH logins through an exchange of public keys. Disabling the root user login through SSH. Now let's create some keys. Creating the user's SSH key set. Each user has the ability to create his or her own set of private and public keys. It doesn't matter whether the user's client machine is running Linux, macOS, Cygwin on Windows, or Bash shell for Windows. In all cases, the procedure is exactly the same. There are several different types of keys that you can create, and 3072-bit RSA keys are normally the default. Until very recently, 2048-bit RSA keys were considered strong enough for the foreseeable future. But now, the most recent guidance from the US National Institute of Standards and Technology, NIST, says to use either an RSA key of at least 3072 or an elliptic curve digital signature algorithm, ECDSA, key of at least 382 bits. You'll sometimes see these ECDSA keys referred to as P384. The reasoning is that they want to get us ready for quantum computing, which will be so powerful that it will render any weak encryption algorithms obsolete. Of course, quantum computing isn't practical yet, and so far it seems to be one of those things that it's always just 10 years off in the future, regardless of what year it is. But even if we discount the whole quantum thing, we still have to acknowledge that even our current non-quantum computers keep getting more and more powerful. So it's still not a bad idea to start going with stronger encryption standards. To see the NIST list of recommended encryption algorithms and recommended key lengths, go to. For these next few demos, let's switch over to an Ubuntu 22.04 client. To create a 3072-bit RSA key pair, just do this, SSH keygen. We don't have to use any option switches because the command will already create the 3072-bit RSA pair by default. When prompted for the location and name of the keys, I'll just hit the enter key to accept the default. You could just leave the private key with a blank passphrase, but that's not a recommended practice. That's because if you get up and leave your workstation while it's running, someone could come along and easily access your private keys, which would allow them to access the service that you administer. Note that if you choose an alternative name for your key files, you need to type in the entire path to make things work properly. For example, in my case, I could specify the path for Donny RSA keys as home Donny SSH Donny RSA. Also, note that in order to add a key to your session key ring, you'll need to just accept the default key file names, because the SSH add utility that we'll be using won't read key files with non-default file names. I'll explain more about the session keyring and SSH add in just a bit. You'll see new keyrings in the .ssh directory, ls-l.ssh. The ID RSA key is the private key with read and write permissions only for me. The ID RSA public key has to be world readable. For ECDSA keys, the default length is 256 bits. If you choose to use ECDSA instead of RSA, do the following to create a strong 384-bit key. SSH keygen -t ECDSA-B 384. Either way, when you look in the SSH directory, you'll see that the ECDSA keys are named differently from the RSA keys. ls-l. The beauty of elliptic curve algorithms is that their similarly short key lengths are just as secure as RSA keys with longer key lengths. And even the largest ECDSA keys require less computing power than RSA keys. The maximum key length you can have with ECDSA is 521 bits. Yes, read that correctly, it's 521 bits, not 524 bits. So you might be thinking, why don't we just go for the Gusto with 421-bit keys? Well, it's mainly because 421-bit keys aren't recommended by NIST. There's some fear that they may be subject to padding attacks, which could allow the bad guys to break your encryption and steal your data. If you're really curious about how padding attacks work, I'll provide a reference in the further reading section. If you take a gander at the man page for SSH keygen, you'll see that you can also create an ED25519 type of key, which you'll sometimes see referred to as curve 25519. This one isn't included in this list of recommended algorithms and also isn't allowed by the Federal Information Processing Standard FIPS regulation. But there are a couple of reasons why some people like to use it. RSA and DSA can leak private key data when creating signatures if the random number generator of the operating system is flawed. ED25519 doesn't require a random number generator when creating signatures, so it's immune to this problem. Also, ED25519 is coded in a way that it makes it much less vulnerable to side channel attacks. A side channel attack is when someone tries to exploit weaknesses in the underlying operating system rather than in the encryption algorithm. The second reason why some folk like ED25519 is precisely because it's not on the NIST list. These are the folk who, rightly or wrongly, don't trust the recommendations of government agencies. Quite a few years ago, in the early part of the century, there was a bit of a scandal that involved the dual elliptic curve deterministic random bit generator, dual ECDRPG. This was a random number generator that was meant for use in elliptic curve cryptography. The problem was that early on, independent researchers found that it had the capability to have backdoors inserted by anyone who knew about this capability. And it just so happened that the only people who were supposed to know about this capability were the folk who work at the US National Security Agency, NSA. At the NSA's insistence, NIST included dual ECDRPG in the NIST list of recommended algorithms, and it stayed there until they finally removed it in April 2014. You can get more details about this at the following links. There's only one key size for ED25519, which is 256 bits. So to create a curved 25519 key, just do this. SSH keygen T ED25519. Here are the keys that I've created. ls-l. There are, however, some potential downsides to ED25519. First, it isn't supported by all the SSH clients. However, if everyone on your team is using current operating systems that use current SSH clients, this shouldn't be a problem. The second is that it only supports one certain set key length, which is the equivalent of either 256-bit elliptic curve algorithms or 3000-bit RSA algorithm, so it might not be quite as future-proof as the other algorithms that we've covered. Lastly, you can't use it if your organization is required to remain compliant with either NIST recommendations or FIPS requirements. Okay, there is one other type of key that we haven't covered. There's the old-fashioned DSA key, which SSH keygen will still create if you tell it to, but don't do it. The DSA algorithm is old, tricky, and very insecure by modern standards, so when it comes to DSA, just say no. Transferring the public key to the remote server. Transferring my public key to a remote server allows the server to readily identify both me and my client machine. Before I can transfer the public key to the remote server, I need to add the private key to my session keyring. This requires two commands. One command invokes SSH agent, while the other actually adds the private key to the keyring. exec usr bin SSH agent $shell SSH add. Finally, I can transfer my public keys to my Alma Linux 9 server, which is at address 192.168.0.17. SSH copy ID Donny at 192.168.0.17. Normally, you would only create one pair of keys of whichever type you choose. As you can see here, I've created 3 key pairs, one pair of each type. All 3 private keys were added to my session keyring, and all 3 public keys were transferred to the remote server. The next time that I log in, I'll use the key exchange and I won't have to enter a password, SSH. As I mentioned previously, you would normally only create one key pair on your local workstation. However, there are exceptions to the rule. Some administrators prefer to use a different key pair for each server that they administer rather than using the same key pair for all servers. This way, if the private key for one machine gets compromised, it won't necessarily mean that the whole network gets compromised. A handy way to do this is to create keys with file names that match the host names of the respective servers. Then, you can use the -I option to specify which key pair that you want to use. Note that if you create keys with custom file names, you won't be able to add them to the keyring, which means that you'll need to type the password of your private key every time you need to use it. I'll explain more about that in just a bit. In this example, I only have one server, but I have multiple keys of multiple types for it, all with the default file names. Let's say that I prefer to use the ED25519 keys, SSH-I, SSH-ID ED25519. So now you're wondering, how is that secure if I can log in without entering my password? The answer is that once you close the client's machine terminal window that you use for login, the private key will be removed from your session keyring. When you open a new terminal and try to log in to the remote server, you'll see this, SSH. Now, every time I log into the server, I need to enter the passphrase of my private key until I add it back to the session keyring with the two commands that I showed you in the preceding section. This all sounds good, but you might know that there's a bit of a caveat. That is, this procedure only works if you create keys with their default file names. If you create keys with custom file names, such as server1ID RSA, for example, the SSH add utility will refuse to read them, and there's no option switch that will make it read them. So you won't be able to add these custom keys to your session keyring, which means that you won't be able to transfer them to the target server with the SSH copy ID. You can still use keys with custom file names, but you'll need to use another means of transferring the public keys to the target server. For example, let's say that you create a pair of keys that you've named Ubuntu1 ID RSI that you want to use to log in to an Ubuntu server. Now, after you created a key, you can use normal SCP to transfer it, like so. cd SSH SCP are Ubuntu1 ID RSA.pub. Next, I'll go over to the Ubuntu1 machine and copy the contents of this public key file to the authorized keys file, like so. ls-l cat Ubuntu1 ID RSA.pub greater than sign SSH authorized keys. By using the single greater than operator in this command, I created a whole new authorized keys file. If you already have an authorized keys file that you want to keep, use the greater operator instead, so that the contents of your public key file will be appended to the end of the existing authorized keys file. Also, be aware that since you can't add keys with custom file names to your session keyring, you won't be able to do passwordless logins. Instead, you'll just be prompted for the private key password every time. Hands-on lab, creating and transferring SSH keys. In this lab, you'll use one virtual machine as your client and one virtual machine as the server. Alternatively, if you're using a Windows host machine, you can use Cygwin, PowerShell, or the built-in Windows Bash shell for the client. Be aware, though, that PowerShell and the Windows Bash shell store the key files in alternate locations. If you're on either a Mac or a Linux host machine, you can use the host machine native command line terminal as the client. In any case, the procedure will be the same. For the server virtual machine, use either Ubuntu 22.04 or CentOS 7. This procedure does work the same on Alma Linux 8 and 9. However, we'll be using this same VM for the next few labs, and Alma Linux has some special considerations that we'll look at later. Let's get started. On the client machine, create a pair of 384-bit elliptic curve keys. Accept the default file name and location and create a passphrase. SSH Keegan T ECD SA B384. Observe the keys, taking note of the permission settings, LSL SSH. Add your private key to your session keyring. Enter your passphrase when prompted. exec usr bin SSH agent $shell SSH add. Transfer the public key to the server VM. When prompted, enter the password for your user account on the server VM. Substitute your own username and IP address in the following commands. SSH copy ID Donny at 192.168.0.7. Log into the server VM as you normally would. SSH Donny 192.168.0.7. Observe the authorized keys file that was created on the server virtual machine. ls-l.ssh cat.ssh/authorized keys. Log out of the server virtual machine and close the terminal window on the client. Open another terminal window and try to log into the server again. This time you should be prompted to enter the passphrase for your private key. Log back out of the server VM, then add your private key back to the session keyring of your client. Enter the passphrase for your private key when prompted. exec usr bin ssh agent greater $shell ssh add. As long as you keep this terminal window open on your client, you'll be able to log into the server VM as many times as you want without having to enter a password. However, when you close the terminal window, your private key will be removed from your session keyring. Keep your server VM because we'll do more with it in a bit. Keep the server VM because we'll do more of it in a bit. You've reached the end of the lab. Congratulations. What we've done here is good, but still not quite enough. One flaw is that if you go to another client machine, you'll still be able to use the normal username password authentication to log in. That's okay, we'll fix that in a few moments. Disabling root user login. A few years ago, there was a somewhat celebrated case where malicious actors had managed to plant malware on quite a few Linux servers somewhere in Southeast Asia. There were 3 reasons that the bad guys found this so easy to do. The internet-facing servers involved were set up to use username password authentication for SSH. The root user was allowed to log in through SSH. User passwords, including the root user's passwords, were incredibly weak. All this meant that it was easy for the Hail Mary botnet to brute force its way in. Different distros have different default settings for root user login. In the etc ssh config file of your CentOS 7 or Alma Linux 8 machine, you'll see this line. Permit root login, yes. Unlike what you have in most common configuration files, the commented out lines in SSH config define the default settings for the secure shell daemon. So this line indicates that the root user is indeed allowed to log in through SSH. To change that, I'll remove the comment symbol and change the setting to no. Permit root login, no. To make the new setting take effect, I'll reload the SSH daemon, which is named SSHD on CentOS and Alma Linux, and is named SSH on Ubuntu. Sudo systemctl reload SSHD. On the Ubuntu machine, the default setting looks a bit different. Permit root login prohibit -password. This means that the root user is allowed to log in, but only via a public key exchange. This is probably secure enough if you really need to allow the root user to log in, but in most cases you want to force admin users to log in with their normal user accounts and use sudo for the admin needs. So in most cases you still want to change the setting to no. On your Alma Linux 9 machine, you will see that it also has the permit root login set to prohibit password by default. Be aware that if you deploy a Linux instance on a cloud service, such as Rackspace or Vultr, the service owners will have you log in to the VM with the root user account. The first thing you'll want to do is create your own normal user account, log back in with that account, disable the root user account, and disable the root user login in SSH config. Microsoft Azure is one exception to this rule because it automatically creates a non-privileged user account for you. You'll be able to practice this in just a few moments in the next section. Disabling username password logins. This is something that you'll only want to do after you set up the key exchange with your client. Otherwise, clients will be locked out of doing remote logins. Hands-on lab, disabling root login and password authentication. For this lab, use the same server VM that you used for the previous lab. Let's get started. On either an Ubuntu, CentOS, or Alma Linux 8 server VM, look for this line in the SSH config file. Password authentication, yes. Remove the comment symbol, change the parameter value to no, and reload the SSH daemon. The line should now look like this. Password authentication, no. Now, when the botnets scan your system, they'll see that doing a brute force password attack would be useless. They'll then just go away and leave you alone. Look for either of these 2 lines, depending on whatever the server is, on Ubuntu or CentOS 7 or Linux VM. Permit root login, yes. Permit root login prohibit password. Uncomment the line and change it to the following. Permit root login, no. Reload the SSH daemon so that it will read in the new changes. On Ubuntu, do this. Sudo systemctl reload SSH. On CentOS Alma Linux, do this. Sudo systemctl reload SSHD. Attempt to log into the server VM from the client that you used in the previous lab. Attempt to log in from the server VM from another client on which you haven't created a key pair. You shouldn't be able to. As before, keep the server VM because we'll do more with it in a bit. You reached the end of the lab. Congratulations. Now that we covered how to create a private public key pair on the client side and how to transfer the public key to the server, let's talk about setting up two-factor authentication. Enabling two-factor authentication. Enabling two-factor authentication. Two-factor authentication can provide an extra layer of protection. If you own a smartphone, you can set this up with Google Authenticator, which will present you with a one-time password for logging in at a local terminal, invoking a sudo command, or logging in remotely via SSH. Before we get started though, there are a few caveats that you need to understand. To make this work on a Linux machine, you'll need to install a PAM module that isn't supplied by Google. It's in repositories for some, but not all the Linux distros. Of course, you could download the source code from the GitHub repository and compile it yourself, but it's beyond the scope of this book. The creator of this PAM module has created some semblance of documentation, but it's not very useful. If you search for documentation, you'll find some blog posts with procedures that are worse than useless because they will break your system if you follow them. You can set up your machine to require Google Authenticator for either global usage or for just logging in via SSH. Global usage means that an authenticator code will be needed for logging in at a local terminal using sudo and logging in remotely via SSH. If you're dealing with multiple users, each user will need to set up Google Authenticator for his or her own user account with his or her own smartphone. Now, with that out of the way, let's set up our Ubuntu 22.04 server with Google Authenticator for local logins and sudo. Note that this PAM module is in the normal Ubuntu repository and in the EPEL repository for RHEL 8 type distros. It's not available at all for RHEL 9 type distros. Hands-on lab, setting up two-factor authentication on Ubuntu 22.04. For this lab, start with a fresh Ubuntu 22.04 virtual machine that's not set up for publicly authentication. That will save a lot of confusion when going through this procedure. Install Google Authenticator on your smartphone. It's in the normal app stores for both Android and iPhone. On your Ubuntu VM, install the libpam Google Authenticator package like this. Sudo apt install libpam Google Authenticator. For these steps, if you haven't already, use SSH to remotely log into the Ubuntu VM from the GUI type terminal of your host machine. That's because you might need to resize things to make the next step work. Now, from this GUI type terminal, run the Google Authenticator app like so, Google Authenticator. A big QR code will now show up on your screen. If the whole code graphic isn't visible, use your GUI terminal controls to zoom out until the whole graphic is visible. Bring up the Google Authenticator app on your smartphone and touch the plus sign in the lower right hand corner of the screen. Choose the Scan QR code option and then take a picture of your QR code. On your smartphone, note that a new entry for Ubuntu VM has been added to the list. On the Ubuntu VM, enter the verification code that shows up with that entry. The next thing you'll see on the Ubuntu terminal is your emergency scratch codes. Copy them down and store them in a safe location. If you lose your mobile phone, you'll use these scratch codes to log in. Next, you'll be asked a series of questions. Just enter yes for everything. In this step, you'll set up two-factor authentication for logging in at the local terminal and for using sudo. Open the etc.pam.d common auth file in your favorite text editor. Add the auth required PAM Google Authenticator.so line as the first parameter. The top portion of the file should now look something like this. Certain blog posts that you'll find tell you to add this line to the end of the file. Be aware that if you do that, you will get locked out of your machine and you will need to perform an emergency procedure to get back in to fix it. Anytime you edit a PAM file, it's vitally important that you place the directives in the proper order. In case you're wondering, I'll show you the emergency procedure in Chapter 16, Security Tips and Tricks for the Busy Bee. At the local terminal of the Ubuntu VM, log out and then log back in. When prompted, enter the verification code from your smartphone app. Perform a command that requires sudo privileges. You should see something like this. Sudo nft list rule set. Note that you won't be required to enter a verification code again until the sudo timer times out. From either your host machine or another VM, remotely log into the Ubuntu VM via SSH. You should still be able to do that because we haven't yet configured the etc sshd config file. Open the sshd config file in your text editor and change the KBD interactive authentication line to KBD interactive authentication yes. Reload the secure shell configuration, sudo systemctl reload SSH. Try logging in again from either your host machine or another VM. This time you should be prompted to enter your verification code. Now let's say that your organization needs two-factor authentication for remote SSH logins but doesn't need it for either local logins or sudo operations. Let's change the configuration so that only remote users will need to enter a code. Open the etc pam.d common auth file in your text editor and remove the line that you inserted in step 9. Open the etc pam.d sshd file in your text editor and add that line just under the include common auth line. At the top of the file, the top portion of the file should now look like this. You should now be able to log into the local terminal and perform sudo actions without having to enter a verification code. Instead, you should only have to enter a verification code when logging in remotely. End of lab. Next, let's look at using Google Authentication together with Key Exchange on our Ubuntu machine. Hands-on lab using Google Authenticator with Key Exchange on Ubuntu. For this lab, use the same Ubuntu VM that you used for the previous lab. On either your host machine or another VM, create a pair of keys and transfer them to the Ubuntu VM as you did in the creating and transferring SSH keys lab. This time you should be prompted to enter a verification code when you execute the SSH copy ID command. On the Ubuntu VM, open the etc sshd config file in your text editor. This time, instead of changing the password authentication yes line, add this line below the KBD interactive authentication yes line. Authentication methods, public key, keyboard-interactive, column PAM. After reloading the SSH configuration, you'll see that you'll be able to remotely log in by using Key Exchange if you log in from a machine that has set up. If you're logging in from a machine that doesn't have Key Exchange set up, you'll still be able to log in with a password and a verification code. So we don't have true two-factor authentication just yet. To require both key-based authentication and Google Authenticator verification, change the above line to look like this. Authentication methods, public key, keyboard interactive PAM. After reloading the SSH configuration, you'll only be allowed to log in from machines for which you've set up a Key Exchange. You now effectively have three-factor authentication because you'll still be prompted to enter your normal login password. To disable the password login so that you'll only be using Key Exchange in the verification code, open the etc pamd sshd file in your text editor. At the very top of the file, find the include common auth line and change it to include common auth. To disable the password login so that you'll only be using Key Exchange and the verification code, open the etc pamd sshd file in the text editor. At the very top of the file, find the include common auth line and change it to include common auth. Verify that the Key Exchange works by trying to log in from a VM on which you haven't performed the Key Exchange setup. You shouldn't be allowed to. That's it, end of the lab. Now let's see what we can do with Alma Linux 8. Hands-on lab setting up two-factor authentication on Alma Linux 8. For this lab, I'll assume that you've already installed the Google Authenticator app on your smartphone. The Authenticator PAM module isn't in any of the repositories for the RHEL 9 distros, but it is in their EPUB repository for their RHEL 8 distros. That might change by the time you read this, so it won't hurt to check if you want to try this on Alma Linux 9. So, fire up a fresh Alma Linux 8 VM and let's get started. Install the PAM module like this. Sudo dnf install ePro release, sudo dnf install Google Authenticator QR encode -libs. Note that you need the QR code -libs package in order to produce a QR code. From the GUI terminal of your host machine, use SSH to remotely log into the Alma Linux 8 VM. This will allow you to resize the QR code image so that you can take a picture of it with your smartphone, then run the Google Authenticator, Google Authenticator-ls SSH Google Authenticator. This time we're creating the Google Authenticator file with thin the SSH directory because Alma Linux is set up to use SE Linux. When you try to log in remotely with Authenticator enabled, the SSH daemon will try to write the Google Authenticator file. SE Linux prevents SSH from writing to files that are outside the SSH directory. We'll talk more about SE Linux in Chapter 10, implemented mandatory access control with SE Linux and App Alma. Follow through on the Authenticator setup, the same as you did in steps 4 through 8 of the setup, setting up two-factor authentication on the Ubuntu 22.04 lab. Open the etc pumd sshd file in your text editor at this line to the very bottom of the file. Auth require pam google authenticator.so, secret home user ssh google authenticator. Note that the line wraps up around on the printed page. Open the etc ssh sshd config file in your text editor, find the line that says challenge response authentication no, and change it to challenge response authentication yes. Reload or restart the SSHD service. Sudo systemctl reload SSHD. Set the proper SE Linux security context on the Google Authenticator file that you created. cd sudo restore con ssh Google Authenticator. Log out of the remote session and try logging back in. This time you should be prompted to enter a verification code. Next, let's set Alma Linux up for using key exchange. Hands-on lab using Google Authenticator with key exchange on Alma Linux 8. This will mostly be the same as it was for Ubuntu, with only a few differences. Transfer the public key from your host machine to the Alma Linux 8 machine as you did in the creating and transferring SSH keys lab. In the etc ssh sshd config file, change the password authentication yes line to password authentication no, and reload the SSH configuration. Now you'll only be using key exchange to log in, which will completely bypass the authenticator. Let's fix things so that you'll be using both. And the etc ssh sshd config file, add the following line just beneath the password authentication no line. Authentication methods: public key password, public key, keyword, interactive. After reloading the SSH configuration, you'll have three-factor authentication because you'll need to enter both your password and a verification code along with the key exchange. If desired, you can easily disable the password prompt and just use the key exchange and verification code. In the etc pamd sshd file, find the auth substack password auth line at the top of the file and change it to auth substack password auth. That's all there is to Google Authenticator. In the next section, let's make sure that we're only using the strongest encryption algorithms. Configuring secure shell with strong encryption algorithms. As I mentioned previously, the current set of NIST recommendations, the Commercial National Security Algorithms Suite, CNSA Suite, involves using stronger algorithms and longer keys than what we need to use previously. I'll summarize the new recommendations here in this table. In other publications, you might see that NIST Suite B is the recommended standard for encryption algorithms. Suite B is an older standard that has been replaced by the CNSA Suite. Another cryptographic standard that you might have to work with is the Federal Information Processing Standard, FIPS, which is also promulgated by the US government. The current version is FIPS 140.3, which gained final approval in September 22, 2019. Understanding SSH encryption algorithms. SSH works with a combination of symmetric and asymmetric cryptography, similar to how Transport Layer Security (TLS) works. The SSH client starts the process by using the public key method to set up an asymmetric session with an SSH server. Once the session has been set up, the two machines can agree on and exchange a secret code, which they'll use to set up a symmetric session. As we saw previously with TLS in Chapter 6, Encryption Technologies, we want to use symmetric cryptography for performance reasons, but we need an asymmetric version to perform the secret key exchange. To perform this magic, we need 4 classes or encryption algorithms, which we'll configure on the server side. These are ciphers. These are the symmetric algorithms that encrypt the data that the client and server exchange with each other. Host key algorithms. This is the last list of host key types that the server can use. Kex algorithms. These are the algorithms that the server can use to perform the symmetric key exchange. MAC. Message authenticating codes are hashing algorithms that cryptographically sign the encrypted data in transit. This ensures data integrity and will let you know if someone has tampered with your data. The best way to get a feel for this is to look at the SSH config man page like this, man sshd conf. I could use any VM to demo this. For now though, I'm going with CentOS 7 unless I state otherwise. The list of default and available algorithms will be different for different Linux distros and versions. Also, note that to demo this, we want to look at the SSHD config man page to see the list of algorithms that are available and enabled. The enabled list is in the man pages for CentOS 7 and normal Linux 8, but not in the man page for normal Linux 9. First, let's look at the list of supported ciphers. Scroll down the man page until you see them. However, not all of these supported ciphers are enabled. Just below this list, we can see the list of ciphers that are enabled by default. Next, in alphabetical order, are the host key algorithms. The list on CentOS 7 looks like this. Next, scroll down to the KEX algorithms, short for key exchange algorithm section. You'll see a list of supported algorithms which looks like this. Be aware that this list can vary from one distro to the next. For example, RHEL 8 or Linux 8 supports 3 additional algorithms that are newer and stronger. Its list looks like this. You'll see the same list on an old Linux 9 machine, except that the strip761x25519 SHA-512 and OpenSSH.com algorithm has been added. Next, you'll see the list of algorithms that are enabled by default. The list can also vary from one Linux distro to another. In this case, though, there's no difference between CentOS 7 and old Linux 8. Finally, we have the Mac algorithms. The default list of enabled algorithms looks like this on CentOS 7. To see the list of algorithms that your particular system supports, either look at the SSH-config man page for that machine or perform the following SSHQ command. SSH-Q cipher, SSH-Q key, SSH-Q kex, SSH-Q Mac. When you look in the etc ssh sshd config file, you won't see any lines that configure any of these algorithms. That's because the default list of algorithms is hard-coded into the SSH daemon. The only time you'll configure any of these is if you want to either enable an algorithm that isn't enabled or disable one that is. Before we do that, let's scan our system to see what is enabled and if the scanner can make any recommendations. Scanning for enabled SSH algorithms. We have 2 good ways to scan an SSH server. If your server is accessible via the internet, you can go to the SSH check site at sshcheck.com. Then, just type in either the IP address or hostname of your server. If you change the port from the default port 22, enter the port number as well. When the scan completes, you'll see the list of enabled algorithms along with recommendations on which ones to either enable or disable. If the machine that you want to scan isn't accessible from the internet, or even if it is, you can use a local scanning tool. In the previous edition of this book, we used the SSH scan tool. Sadly, this tool is no longer supported, and it doesn't work on newer Linux distros that come with OpenSSL version 3. So instead, let's try with the Nmap scripting engine. Hands-on lab scanning with Nmap. For this lab, you can use any of your virtual machines. Let's get started. First, install the Nmap package from a normal distro repository. On Ubuntu, do sudo apt update sudo apt install nmap. On CentOS 7, do this, sudo yum install nmap. On normal Linux 8 or 9, do this, sudo dnf install nmap. Use nmap with the ssh2 enum algos NSE script to scan the server VM that you created and configured in the previous labs. Substitute your own IP address for the one I'm using here. Note that even if you haven't created a key pair on the scanner machine, the scan still works against machines that have had username, password authentication disabled, but of course you won't be able to log in from the scanner machine. Nmap script ssh2 enum algos NSE 192.168.0.14. Note that if you're scanning a machine with an enabled firewall, you might get an error message about how the scan has been blocked. If that happens, try adding the pn switch so that the command will look like this. Nmap pn script ssh2 enum algos.nse 192.168.0.14. Repeat the scan, but this time save the output to a normal text file like so. Nmap script ssh2 enum algos nsc 192.168.0.14 on ubuntu scan.txt. Open the text file in a normal text editor or pager. You'll see a complete list of all of the algorithms that are enabled. Compare your results with the standards that are applicable to your circumstances, such as NIST
CNSA standard to be sure that you enabled or disabled the right things. On either your host machine or a VM with a desktop interface, visit the Shodan website at shodan.io, type SSH into the search window and observe the list of internet-facing SSH servers that comes up. Click on different IP addresses until you find an SSH server that's not running on the default port 22. Observe the list of enabled algorithms for that device. Scan the device using the -P switch to scan the different ports like so. nmap-p2222 script ssh enum algos nse 192.168.0.14. Note that in addition to the list of enabled algorithms that you saw on Shodan, you now have a list of weak ones that the owner of this device needs to disable. Keep both the scanner and the server VM handy because we'll use them again after we disable some algorithms. You reached the end of the lab. Congratulations. Okay, let's disable some of the creaky, old and weak stuff. Disabling weak SSH encryption algorithms. As I said before, we want to compare our scan results against the NIST recommendations and configure things accordingly. Understand though that the list of available algorithms differs from the one Linux distro to the next. To make things less confusing, I'll present two hands-on procedures in this section. One is for Ubuntu 22.04 and the other one is for CentOS 7. All my Linux 8 and 9 have their own unique way of doing business, so I'm saving that for the next section. Hands-on lab, disabling weak SSH encryption algorithms Ubuntu 22.04. For this lab, you'll need the VM that you've been using as a scanner and another Ubuntu 22.04 VM to scan and configure. Let's get started. If you haven't done so already, scan the Ubuntu 22.04 VM and save the output to a file. And map script ssh2 enum algos nse 192.168.0.14 and ubuntu scan.txt. Count the number of lines in the file by doing wc-l ubuntu scan.txt. On the target Ubuntu 22.04 VM, open the etc ssh config file in your preferred text editor. Toward the top of the file, find these two lines, ciphers and key limit default none. Beneath those two lines, insert these three lines. In the ciphers and MAC lines, you'll see a comma-separated list of algorithms that were disabled by the preceding dash sign. You only need one dash to disable all the algorithms in the list. In the kex algorithms line, there's no dash sign. This means that the algorithm that's listed on that line is the only one that is enabled. Save the file and restart the SSH daemon. Verify that it started correctly. Sudo systemctl restarts SSH, sudo systemctl status SSH. Scan the Ubuntu 22.04 virtual machine again, saving the output to a different file. And map script ssh2 enum algos nse 192.168.0.14 and ubuntu scan modify.txt. Count the number of lines in the new file, wc-l ubuntu scan modify.txt. On the scanner VM, use dev to compare the two files. You should see fewer algorithms than you saw previously. diff-y ubuntu scan.txt, ubuntu scan modify.txt. The sharp-eyed among you will notice that we left one cipher that isn't on the CNSA list. SHA-20 poly 1305 at openssh.com is a lightweight algorithm that's good for users with low-powered handheld devices. It's a good, strong algorithm that can replace the vulnerable Advanced Encryption Standard AES algorithm, but with high performance. However, if you have to remain 100% compliant with this CNSA standard, then you might have to disable it. You reached the end of lab 7 of lab. Congratulations. Now let's work with CentOS 7. Hands-on lab, disabling weak SSH encryption algorithms, CentOS 7. You notice two things when you start working with CentOS 7. More algorithms enabled. A default SSH configuration of CentOS 7 has a lot more enabled algorithms than what Ubuntu 22.04 has. This includes some really ancient stuff that you really don't want to see anywhere. I'm talking about things such as Blowfish and 3DS, which should have been retired years ago. A different configuration technique on CentOS, placing a dash sign in front of a list of algorithms that you want to disable doesn't work. Instead, you'll need to list all of the algorithms that you want to enable. For this lab, you'll need the CentOS 7 VM and the same scanner VM that you've been using. With that in mind, let's get to work. Scan the CentOS 7 VM and save the output to a file. Note that due to the CentOS 7 firewall, you need to add the -pn option and map -pn script ssh enum algos nse 192.168.0.12 and CentOS 7 scan.txt. Count the number of lines in the output file, wc-l CentOS scan.txt. On the target CentOS 7 VM, open the etc ssh sshd config file in your preferred text editor. Toward the top of the file, find these two lanes. cipher and key limit default none. Beneath those two lines, insert these three lines. As I mentioned previously, with CentOS, using dash to disable algorithms doesn't work. Instead, we have to list all of the algorithms that we do want to enable. Save the file and reload the SSH daemon. Verify that it started correctly. Sudo systemctl reload SSHD, sudo systemctl status SSHD. Scan the CentOS 7 virtual machine again, saving the output to different files. Nmap pn script ssh2 enum algos NSE 192.168.0.12 and CentOS 7 scan modified txt. Count the number of lines in the new output file. wc-l CentOS scan modified txt. On the scanner VM, use diff to compare the two files. You should see fewer algorithms than you saw previously. diff-y CentOS scan.txt, CentOS 7 scan modified txt. As before, I left the SHA-20 poly 1305 OpenSSH.com algorithm enabled. If you want to remain 100% compliant with the NIST and CMSA standards, then you might have to disable it. You reached the end of the lab. Congratulations. Now let's look at a handy new feature that comes with the RHEL 8 and 9 families. Setting system-wide encryption policies on RHEL 8.9 and all Linux 8.9. In Chapter 6, Encryption Technologies, we briefly looked at how to set up system-wide encryption policies on all Linux 8 and 9. With this cool feature, you no longer have to configure crypto policies for each individual daemon. Instead, you just run a couple of simple commands and the policy is instantly changed for multiple daemons. To see which daemons are covered, look in the etc crypto policies backends directory. See, here's a partial view of what's there. ls-l. As you see, this directory contains symbolic links to text files that contain directives about which algorithms to either enable or disable for the default configuration. One level up, in the etc crypto policies directory, there's the config file. Open it, and you'll see that this is where the system-wide configuration is set, default. Scanning this VM with its default configuration shows that quite a few older algorithms are still enabled. To get rid of them, we can change to either future mode or to FIPS mode. At the time of this writing, the EPL repository uses a security certificate that's not compatible with future mode. This will prevent you from updating or installing any software packages from the EPL repository. If you need to set up your machine with both future mode and the EPL repository, be aware that you'll need to set the machine back to default mode before you can either fully update your system or install packages from EPL. Of course, this problem could be fixed by the time we read this. To show you how this works, let's get our hands dirty with another lab. Hands-on lab. Setting encryption policies on ALM Linux 9. Start off with a fresh ALM Linux 9 VM and the scanner VM that you've been using. Now follow these steps. On an ALM Linux 9 VM, use the update crypto policies utility to verify that it's running in default mode. Sudo update crypto policies show. Scan the ALM Linux 9 VM and its default configurations and save the output to a file. Nmap pn script ssh2 enum algos.nse 192.168.0.17 and alma9 default txt. On the ALM Linux 9 virtual machine, set a system-wide crypto policy to future. Sudo update crypto policies set future. In the etc ssh directory, remove the current host machine keys. Sudo rm etc ssh key. Don't worry, new keys will get created when you reboot the machine. Reboot the VM, sudo shutdown-r now. On the scanner VM, open the SSH GNOME host file in the text editor, delete the entry that was previously made for the ALM Linux 9 VM and save the file. We have to do this because the public key fingerprint on the ALM Linux VM will have changed because of the new policy. Scan the algorithm VM, the ALM Linux VM again, saving the output to a different file, nmap-pn script ssh2 enum algos NSE 192.168.0.17 or and ALM Linux 9 future txt. Compare the two output files. You should now see fewer enabled algorithms than you did previously. diff-y ALM Linux 9 default txt alma9-future txt. Look at the files in the etc crypto policy backends directory, ls-l etc crypto policies backends. You'll now see that the symbolic links point to files in the future directories. Look at the host keys in the etc ssh directory and see if they differ from what you had before. ls-l etc ssh key. Scan the ALM Linux 9 VM that is set up in FIPS mode for the lab in Chapter 6 Encryption Technologies. Compare the results with the default and future mode scans. End of lab. If future mode hasn't disabled enough algorithms for you, you can always just create your own custom policy. See the details here. Now you know how to configure SSH to use only the most modern, most secure algorithms. Next, let's look at logging, configuring the more detailed logging. In its default configuration, SSH already creates log entries whenever someone logs in via SSH, SCP, or SFTP. On Debian Ubuntu systems, the entry is made in the var log of the log file. On Red Hat, CentOS, or Linux systems, the entry is made in the var log secure file. Either way, the log entry looks something like this. Open the SSH config command page and scroll down to the log level item. There you'll see the various settings that provide different levels of detail for logging SSH messages. The levels are as follows: quiet, fatal, info, verbose, debug or debug 1, debug 2, debug 3. Normally the only two of these we would care about are info and verbose. Info is the default setting, while verbose is the only other one that we would use under normal circumstances. The various debug levels might come in handy for troubleshooting, but the man page warns us that using debug in production settings would violate others' users' privacies. Let's go ahead and get our hands dirty just to get a feel of what gets logged with the various levels. Hands-on lab configuring more verbose SSH logging. For this lab, use the same VM that you've been using for the previous labs. That way you'll get a better picture of what a complete SSHD config file should look like when it's fully locked down. Remotely log in to the target VM via SSH and follow these steps. Open the main log file and scroll down to where you see the entry that was made due to your login and observe what it says. For Ubuntu, do sudo less varlog author log. For CentOS or Linux, do sudo less varlog secure. As I mentioned previously, you never want to run the production machine with SSH log levels set to any of the debug levels, but just so you can see what it does. Log, set your machine to debug now. Open the etc sshd config file in your favorite text editor. Find the line that says the following: log level info, change it to the following: log level debug 3. After saving the file, reload SSH. On Ubuntu, do sudo systemctl reload SSH. On CentOS or Linux, do this: sudo systemctl reload SSHD. Log out of the SSH session and then log back in. View the system log file to see the new entries from this new login. Open the etc sshd config file for editing. Change the log level debug 3 line to the following: log level verbose. After saving the file, reload or restart the SSH daemon. Log out of the SSH session, log back in, and look at the entries in the system log file. The main benefit of verbose mode is that it will log the fingerprints of any key that was used to log in. This can be a big help with key management. You'll reach the end of the lab. Congratulations. So you just seen how to get more information about SSH logins in your system logs. Next, let's talk a bit about access control, configuring access control with whitelist and TCP wrappers. We already locked things down pretty well just by requiring the clients to authenticate via key exchange rather than by username and password. When we prohibit password authentication, the bad guys can do brute force attacks against us until the cows come home, and it won't do them any good. Although in truth, they'll just give up as soon as they'll find that password authentication has been disabled. For an extra measure of security, we can also set up a couple of access control mechanisms that will allow only certain users groups or client machines to log into an SSH server. The two mechanisms are whitelist within the SSHD config file, TCP wrappers via the etc.host.allow and the etc.host.deny files. Okay, now you're now saying, but what about firewalls? Isn't that a third mechanism that we can use? And yeah, you're right, but we already covered firewalls in Chapter 4, Security Server, with as Firewall Part 1, and Chapter 5, Security Server with Firewall Part 2, so I won't repeat any of that here. You can also place access control directives in your system unit files for SSH. For our present discussion, though, I'd rather avoid the complexities of explaining how to edit a systemd unit file. At any rate, these are the ways of controlling access to your SSH server. You can use all of them together if you really want to, or you can just use one of them at a time. It really depends on just how paranoid you are. There are two competing philosophies about how to do access control. With Blacklist, you specifically prohibit access by certain people or machines. That's difficult to do because the list could get very long and you still won't block everybody that you need to block. The preferred and easier method is to use whitelist, which specifically allow access to certain people or machines. First, let's look at creating whitelist or within SSHD config with a hands-on lab. Configuring whitelist within SSHD config. The 4 access control directives that you can set within SSHD config are as follows: deny users, deny groups, allow groups. For each directive, you can specify more than one username or group name, separating them with a blank space. Also, these 4 directives are processed in order that I've listed them here. In other words, if a user is listed with both the deny users and the allow users directives, the deny user takes precedence. If a user is listed with deny user and is a member of a group that's listed with allow groups, the deny user again takes precedence. To demonstrate this, let's do allow. Hands-on lab configuring whitelist within SSH config. This lab will work on any of your VMs. Follow these steps. On the VM that you wish to configure, create user accounts for Frank, Charlie, and Maggie. On Ubuntu, do it like this: sudo add user Frank. On CentOS and all Linux, do it like this: sudo user add Frank, sudo password Frank. Create the web admins group and add Frank to it. Sudo group add web admins, sudo user mod -a-g web admins Frank from either your host machine or from another VM. Have the 3 users log in, then log them back out. Open this etc sshd config file in your favorite text editor. At the bottom of the file, add an allow users line with your own username, like so: allow users Donny. Then restart or reload the SSH service and verify that it has started correctly. For Ubuntu, sudo systemctl restart SSH, sudo systemctl status SSH. For CentOS, sudo systemctl restart SSH D, sudo systemctl status SSH D. Repeat step 3. This time, these 3 kitties shouldn't be able to log in. Open the etc sshd config file in your text editor. This time, add an allow groups line to the bottom of the file for the web admins group, like so: allow groups web admins. Restart the SSH service and verify that it started properly. From either your host machine or another VM, have Frank try to log in. You'll see that even though he's a member of the web admins group, he'll still be denied. That's because the allow users line with your own username takes precedence. Open SSHD config in your text editor and remove the allow users line that you've inserted in step 4. Restart the SSH service and verify that it started properly. Try to log into your own account and then try to log into the accounts of all the other users. You should now see that Frank is the only one who is allowed to log in. The only way that any of the other users can now log in into the VMs is from the VM's local console. Log into your own account and at the VM's local console, delete the allow groups line from sshd config, restart the SSH service. You've reached the end of the lab. Congratulations. You've just seen how to configure a whitelist at the daemon level using the SSH daemon's own configuration file. Next, we'll look at configuring whitelist at the network level, configuring whitelist with TCP wrappers. It's a strange name, but it's a simple concept. TCP wrappers, singular, not plural, listens to incoming network connections and either allows or denies connection requests. Whitelist and blacklist are configured in the etc host.allow file and the etc host.deny file. Both of these files work together. If you create a whitelist in host.allow without adding anything to host.deny, nothing will be blocked. That's because TCP wrappers consults host.allow first, and if it finds a whitelisted item there, it will just skip overlooking host.deny. If a connection request comes in for something that isn't whitelisted, TCP wrappers will consult host.allow, find that there's nothing there for the source of this connection request, and then will consult host.deny. If nothing is in host.deny, the connection request will still go through. So, after you configure host.allow, you have to also configure host.deny in order to block anything. You'll want to note that the Red Hat fork have stripped TCP wrappers from RHEL 8.9 and their offspring. So if you decide to practice with the technique that I presented here, you can do so with either your Ubuntu or CentOS 7 VMs, but not on your own 8.9 VMs. The Red Hat fork now recommend doing access control via firewall D rather than TCP wrappers. You can read about it here. You'll need a Red Hat account to read the whole article. If you don't need to pay for Red Hat support, you can open a free of charge developer's account. Now here's something that's extremely important. Always configure host.allow before you configure host.deny. That's because as soon as you have saved either of these files, the new configuration immediately takes effect. So if you configure the blocking rule in host.deny while logged in remotely, your SSH connection will break just as soon as you save the file. The only way to get back in will be to enter the server room and reconfigure things from the local console. Your best bet is to get used to the idea of always configuring host.allow first, even when you're working from the local console. That way you'll always be sure. Amazingly though, there are other TCP wrappers tutorials out there that tell you to configure host.deny first. What are these guys thinking?
You can do some rather fancy tricks with TCP wrappers, but for now I just want to keep things simple, so let's look at some of the most used configurations. To whitelist a single IP address, place a line like this into the etc host allow file, sshd column 192.168.0.255. Then place this line into the etc host deny file, sshd all. Now, if you try to log in from anywhere else besides the IP address that's listed in the host.allow, you will be denied access. You can also list either multiple IP addresses or multiple network addresses in the host.allow. For details on how to do this, see the host.allow man page. As I mentioned previously, you can do some fancy things with TCP wrappers, but now that the Red Hat fork have deprecated, you should probably get used to the idea of either setting up file rules or configuring the SSHD config file. On the other hand, TCP wrappers could come in handy whenever you need to configure an access control rule very quickly, provided that you are on a machine that supports it, configuring automatic logout and security banners. Best security practice dictates that people log out of their computers before they walk away from the desk. This is especially important when an administrator uses his or her cubicle computer to remotely log into a sensitive server. By default, SSH allows a person to remain logged in forever without complaining. However, you can set it up to automatically log out idle users. We'll look at two quick methods for doing that. Configuring automatic logout for both local and remote users. This first method will automatically log out idle users while logged in either at the local console or remotely via SSH. Go to the etc profile.d directory and create the autologout.sh file with the following contents. tmout equals 100, read only, tmout, export, tmout. This sets a timeout value of 100 seconds. Tmout is a Linux environmental variable that sets timeout values. Set the executable permission for everybody, sudo chmod +x autologout.sh. Log out and then log back in. Then let the VM sit idle. After 100 seconds, you should see that the VM is back at the login prompt. Note though, that if any user is already logged in at the time you create the file, the new configuration won't take effect for them until they are logged out and then logged back in. Configuring automatic logout in SSHD config. The second method only logs out users who are logged in remotely via SSH. Instead of creating the etc profile.d autologout.sh file, look for these two lines in the etc ssh sshd config file. Client alive interval 0. Client alive count max 3. Change them to the following: client alive interval 100, client alive count max 0. Then restart or reload the SSH service to make the change take effect. I've used 100 seconds for the timeout value in both of these examples. However, you can set the timeout value to suit your own needs. You now know how to automatically log out your users. Now let's look at setting up security banners. Creating a pre-login security banner. In Chapter 3, Securing Normal User Accounts, I showed you how to create a security message that shows up after the user has logged in. To do this, by inserting a message into the etc motd file. But when you think about it, wouldn't it be better for people to see a security banner before they log in? You can do that with sshd config. First, let's create a etc sshd banner file with the following content. Warning, authorized users only, or others will be prosecuted. In the etc sshd config file, look for this line, banner none. Change it to this, banner /etc sshd banner. As always, restart and reload the SSH service. Now, whoever logs in remotely will see something like this. SSH Donny at 192.168.0.3. So, will this banner keep your system safe and secure for the bad guys? No. But it could be useful if you ever have to take the case to court. Sometimes it's important to show a judge and jury that the intruders knew that they were going where they don't belong. Now that you know how to set up security banners and automatic logouts, let's look at a few miscellaneous settings that don't fit neatly into any one category. Configuring all the miscellaneous security settings. Our SSH configuration is a lot more secure than it used to be, but we can still make it better. Here are a few little tricks that you might not have seen elsewhere. Disabling X11 forwarding. When you SSH into a server in a normal manner, as we've been doing, you can only run text mode programs. If you try to remotely run any GUI-based programs such as Fireworks, you'll get an error message, but when you open the SSH config file of pretty much any Linux distro, you'll see this line, X11 forwarding, yes. This means that with the right option switch, you can remotely run GUI-based programs, assuming that you're logging into a machine that has a graphical desktop environment installed. You can use either the -I or the -X option when logging in, like so. SSH-X Donny at 192.168.0.12 or SSH-Y Donny at 192.168.0.12. The problem here is that the X11 protocol, which powers graphical desktop environments on most Linux and Unix systems, has a few security weaknesses that make it somewhat dangerous to use remotely. The bad guys have ways of using it to compromise their entire system. Your best bet is to disable it by changing the X forwarding line to look like this. X11 forwarding, no. As usual, restart or reload the SSH service to make it read in the new configuration. Know that you know about XSS forwarding list sticks and tunnels. Disable SSH tunneling. SSH tunneling, or as it's sometimes called SSH port forwarding, is a handy way to protect non-secure protocols. For example, by tunneling normal HTTP through an SSH tunnel, you can access a non-secure website in a secure fashion. Here's what it looks like. Sudo ssh-l at column localhost column 80 Donny at 192.168.0.12. I had to use sudo here because all network ports below port 1024 are privileged ports. If I were to change the web server configuration to listen on a non-privileged high number port, I wouldn't need sudo. Now, just to connect to this site in a secure manner, I can just open a web browser on my local machine and type in the following URL, http ://localhost. Yeah, it seems strange to access a remote machine by typing in localhost, but that's the designator I used when I logged in with SSH. I could have used another name, but localhost is a name you traditionally see in SSH tutorials, so I'm following suit here. Now, as soon as I log out of the SSH session, my connection to the web server will break. Even though this sounds like a good idea, it actually creates a security problem. Let's say that your corporate firewalls are set up to prevent people from going home and remotely logging into their company workstation. That's a good thing, right? Now, let's say that the company firewall has to allow outbound SSH connections. A user could create an SSH tunnel from his or her company workstation to a computer at another location, and then go to that location and create a word for reverse tunnel to the company workstation. So, if it isn't possible to block outgoing SSH traffic at a firewall, then your best bet is to disable SSH tunneling. In your SSH config file, ensure that you have lines that look like this. Allow TCP forwarding? No. Allow stream local forwarding? No. Gateway ports? No. Permit tunnel? No. Restart or reload the SSH service as always. Now port tunneling will be disabled. Now that you know how to disable SSH tunneling, let's talk about changing the default port. Changing the default SSH port. By default, SSH listens on port 22 TCP. If you've been around for a while, you've surely seen plenty of documentation about how important it is to use some other port in order to make it harder for the bad guys to find your SSH server. But I must say, this notion is a bit controversial. In the first place, if you enable key authentication and disable password authentication, then changing the password, the port has limited value. When a scanner bots find your server and sees that password authentication is disabled, it will just go away and won't bother you anymore. In the second place, if you were to change the port, the bad guy scanning tools can still find it. If you don't believe me, just go to shodan.io and search for SSH. In this example, someone thought they were smart by changing to port 2211. Figure 701 SSH port on Shodan. Yeah, smarty pants. That didn't hide things so well, now did it? On the other hand, security expert Daniel Miesler says that it's still useful to change the port in case someone tries to leverage a zero-day exploit against SSH. He recently published the results of an informal experiment that he did, in which he set up a public server that listens for SSH connections on both ports 22 and ports 24, and observes the number of connection attempts to each port. He said that over a single weekend there were 18,000 connection attempts to port 22 and only 4 to port 24. But although he doesn't explicitly say, it appears he left password authentication enabled. To have truly scientifically accurate results, he needs to conduct the same study with password authentication disabled. He also needs to conduct the study on separate servers that have SSH enabled for either port 22 or port 24 instead of having both ports enabled on a single machine. My hunch is that when the scanner bots found that port 22 was open, they didn't bother to scan for any other SSH ports. You can read about his experiment here. Anyway, if you do want to change ports, just uncomment the port 22 line in SSHD config and change the port number to whatever you want. Next, let's talk about key management. Managing SSH keys. Earlier, I showed you how to create a pair of keys on your local workstation and transfer the public key to a remote server. This allows you to really disable username password authentication on the server, making it much harder for the bad guys to break in. The other problem with this that we didn't address is that the public key goes into unauthorized key files that's in the user's own home directory, so the user can manually add extra keys to the file, which would allow the user to log in from other locations besides one that's been authorized. And there's also the problem of having authorized keys files all over the place in every user's home directory. That makes it a bit hard to keep track of everyone's keys. One way to handle this is to move everyone's authorized keys file to one central location. Let's take Vicky, my 50-and-a-half-year-old solid grey kitty. The administrator creates an account on the server that she needs to access and allow her to create and transfer her key to it before disabling possible authentication. So Vicky now has her authorized keys file in her home directory on that server, as we see here. cd.ssh ls-l. Vicky owns the file and she has both read and write permissions on it, so even though she can't transfer all the keys to it the normal way once the administrator has disabled password authentication, she can still transfer key files manually and manually edit the authorized keys files to include them. To thwart her efforts, an intrepid administrator will create a directory within the etc.ssh directory to hold everyone's authorized key files, like so. Sudo mcgr etc.ssh authorized keys. Our intrepid administrator's full admin privileges allow him to log into the root user shell, which allows him to go into the directories of all other users. Sudo su-cd home wiki ssh ls-shell. The next step is to move Vicky's authorized keys file to the new location, changing its name to Vicky, like so. Move authorized keys etc.ssh authorized keys /Vicky. Exit. Now we have a bit of a conundrum. As you see here, the file still belongs to Vicky and she has both read and write privileges, so she can still edit the file without any administrator privileges. Removing the write privilege won't work because since the file belongs to her, she could just add the write privileges back. Changing the ownership to the root user is part of the answer, but that will prevent Vicky from being able to read the file, which will prevent her from logging in. To see the whole solution, let's see what I've already done with my own authorized keys file. cd etc.ssh authorized keys ls-l. The eagle-eyed among you have surely noticed what's going on with the Donny file. You see that I changed ownership to the root user and then added an access control list as indicated by the plus sign. Let's do the same for Vicky. Sudo shown root Vicky Looking at the permission settings, we see that Vicky has read access to the Vicky file. ls-l. While we're at it, let's look at her access control list. Vicky can now read the file so that she can log in, but she can't change it. The final step is to reconfigure the SSHD config file and restart or reload the SSH service. Open the file in the text editor and look for this line, authorized key files, SSH, authorized keys, SSH authorized keys 2. Change it to this, authorized keys file, etc SSH authorized keys, %u. The %u at the end of the line is a mini macro that tells the SSH service to look for a keys file that has the same name as the user who's logging in. Now, even if users were to manually create their own authorized keys files in their own home directories, the SSH service would just ignore them. Another benefit is that having the keys all in one place makes it a bit easier for the administrator to revoke someone's access should they need arise. Be aware that there's a lot more to managing SSH keys that I've been able to present here. One problem is that while there are a few different free open source software solutions for managing public keys, there aren't any for managing private keys. A large corporation could have thousands or perhaps even millions of private and public keys in different places. Those keys never expire, so they'll be around forever unless they get deleted. If the wrong people get hold of a private key, your whole network could become compromised. As much as I hate to say it, the best bet for managing SSH keys is to go with a commercial solution, such as ones from SSH.com and CyberArk. Check out the key management solutions from SSH.com here. Read here for CyberArk's key management solutions. Full disclosure, I have no connection with either SSH.com or CyberArk and receive no payment for telling you about them. You've learned several cool tricks here for beefing up your server security. Now let's take a look at how to create different configurations for different users and groups, setting different configurations for different users and groups. On the server side, you can use the matched user or matched group directive to set up custom configurations for certain users or groups. To see how it's done, look at the example at the very bottom of the etc SSHD config file. There you see the following. Of course, this has no effect since it's commented out, but that's okay. Here's what we see if we use the anon CVs. He can't do X11 forwarding, he can't do TCP forwarding, he won't have the use of a command terminal. As soon as he logs in, he'll be starting the current concurrent versioning service CVS server by not having use of the terminal, and on CVS can start the CVS server but can't do anything else. You can set up different configurations for as many users as you need to. Anything that you put in the custom configurations will override the global settings. To set up a custom configuration for a group, just replace match user with match group and supply a group name instead of a username, creating different configurations for different hosts. For a change of pace, let's look at the client end now. This time we'll look at a handy trick to help ease the pain of logging into different servers that require different keys or SSH options. This also allows you to access servers via easy to remember names rather than having to remember multiple server IP addresses. All you have to do is go into the SSH directory in your own home directory and create a config file. To demonstrate this, let's create a configuration that allows us to easily access server 1. In the SSH config file, we can add a stanza that looks something like this. Here's the breakdown. Host, this is the common name that you can use in your login command. Hostname, for this, use either the IP address or hostname of the server. If you use the hostname, it will either have to be registered in DNS or have an entry in your local etc host file. User, you log in as this user. Identity file. This specifies the key that goes with this server. You can use a key with a custom file name if you desire, as long as you don't mind typing in the private key password every time you need to access this server. As a reminder, that's because SSH add won't add keys with custom file names to your session keyring. Identities only yes. If you happen to have more than one key loaded into your session keyring, this forces your client to only use the key that's specified there. Forward X11 yes. We want this client to use X11 forwarding. Of course, this will only be effective if the server has been configured to allow it. Cipher AES256GCM at openssh.com. We want to use this algorithm and only this algorithm to perform our encryption. To create custom configurations for other hosts, just add a stanza for each one to this file. Then, to log in to a server that's listed in this config file, just invoke the SSH command with the desired host designation. For example, to log into Donny's account on server 1, as you see configured above, just do this, SSH server 1. There's a lot more we can do with custom configurations, and I'll leave some references for you in the further reading section. Next, let's talk about SFTP, where we'll make good use of the match group directive that we just looked at. Setting up a root environment for SFTP users. Secure File Transfer Protocol, SFTP, is a great tool for performing secure file transfers. There is a command line client, but users will most likely use a graphical client such as FileZilla. With the default SSH setup, anyone who has a user account on a Linux machine can log in through either SSH or SFTP and can navigate through the server's entire file system. What we really want for SFTP users is to prevent them from logging into a command prompt via SSH and to confine them to their own designated directories. One good use for this trick would be to set up SFTP configurations for website creators. Instead of allowing these users to transfer files to and from their own home directories, just allow them to transfer files to and from the website contents directories instead. Creating a group and configuring the SSHD config file. With the exception of the slight difference in user creation commands, this procedure works the same way on any of your virtual machines. We'll begin by creating an SFTP users group. Sudo add group SFTP users. Create the user accounts and add them to the SFTP users group. We'll do both operations in one step. On your CentOS or Alma Linux machine, the command for creating a Max account would look like this. Sudo user add-g SFTP users max sudo password max. On your Ubuntu machine, it would look like this. Sudo user add-m-d home max-s bin bash
SFTP users max. Open the etc sshd config file in your favorite text editor. Find a line that says this: subsystem sftp user lib OpenSSH SFTP server changes to this: subsystem SFTP internal SFTP. And this setting allows you to disable normal SSH login for certain users. At the bottom of the SSHD config file, add a match group stanza, match group SFTP users to root directory home, allow TCP forwarding no, allow agent forwarding no, X11 forwarding no, force quint internal SFTP. An important consideration here is that the root directory has to be owned by the root user, and it can't be writable by anyone other than the root user. When Max logs in, he'll be in the home directory, and will then means that you want all your users' home directories to have the restrictive 700 permission setting in order to keep everyone out of everyone else's stuff. Save the file and restart the SSH daemon. Then try to log on as Max through normal SSH just to see what happens. SSH max at 192.168.0.8, max at 192.168 password. This device allows SFTP connections only. Connection to 192.168.0.8 closed. Okay, so he can't do that. Now let's have Max try to log in through SFTP and verify that he is in the home directory. SFTP max at 192.168.0.8. So our root tail does indeed work. Hands-on lab, setting up a root directory for the SFTP users group. For this lab, you can use either the CentOS VM or the Ubuntu VM. You will add a group, then configure the SSHD config file to allow group members to only be able to log in via SFTP, and then confine them to their own directories. For the simulated client machine, you can use the terminal of your macOS or Linux desktop machine or any of the available bash shells from your Windows machine. Let's get started. Create the SFTP users group. Sudo group add SFTP users. Create a user account for Max and add him to the SFTP user group. On CentOS or OMA Linux, do this: sudo user add -g SFTP users max sudo password max. On Ubuntu, do this: sudo user add -m-d home max -s bin bash -g SFTP users max. For Ubuntu, ensure that the user's home directories are all set with read, write, and execute permissions for only the directory's user. If that's not the case, do this: sudo change mod 700 home /star. Open the etc sshd config file in your preferred text editor. Find a line that says the following: subsystem sftp user lib OpenSSH SFTP server. Change it to the following: subsystem sftp internal SFTP. At the end of the sshd config file, add this stanza: match group SFTP users, root directory home, allow TCP forwarding no, allow agent forwarding no, X11 forwarding no, force command internal SFTP. Reload the SSH configuration. On CentOS or OMA Linux, do this: sudo systemctl reload SSHD. On Ubuntu, do this: sudo systemctl reload SSH. Have Max try to log in through normal SSH to see what happens. SSH max at IP address of your VM. Now you have Max log in through SFTP. Once he's in, have him try to cd out of the home directory SFTP max at IP address of your VM. You reached the end of the lab. Congratulations! Now that you know how to securely configure SFTP, let's look at how to securely share a directory. Sharing a directory with SSHFS. There are several ways to share a directory across a network. In enterprise settings, you'll find the network file system NFS, Samba, and various distributed file systems. SSHFS isn't used in enterprise quite as much, but it can still come in handy. The beauty of it is that all of its network traffic is encrypted by default, unlike with NFS or Samba, and other than installing the SSHFS client program and creating a local mount point directory, it doesn't require any configuration beyond what you've already done. It's especially handy for accessing a directory on a cloud-based virtual private server, VPS, because it allows you to just create files in the shared directory rather than using SCP or SFTP commands to transfer the files. So if you're ready, let's jump in. Hands-on lab. Creating a directory with SSHFS. For this lab will use two VMs. For the server, you can use any of your VMs. The same is true of the client, except that each distro has the SSHFS client in a different repository. Here's what I'm talking about. The client is in the normal Ubuntu repository, so you don't have to do anything special to get it. For CentOS 7 and all Linux 9, you'll need to install the EPL release package with the normal yum install or DNF install command. Linux 8 has the SSHFS client in its own PowerSuite repository, which isn't enabled by default. To enable it, open the etc yum repos d or Linux PowerTools repo file in your favorite text editor. In the Power Tools section, find the line that says enabled equals 0 and change it to enabled equals 1. Now that we have all that straight, let's get started. Boot up one VM for the server. That's all you need to do for the server end. On the other VM that you'd use as a client, create a mount point directory within your own home directory, like so. Remote. On the client VM, install the SSHFS client. On Ubuntu, do this: sudo apt install SSHFS. On CentOS, do this: sudo yum install fuse SSHFS. On normal Linux or 8 or 9, do this: sudo dnf install fuse SSHFS. From the client machine, mount your own home directory that's on the server. SSHFS Donny at 192.168.0.10 home Donny remote. Note that if you don't specify a directory to share, the default is to share the home directory of the user who is logging in. Verify that the directory was mounted properly with the mount command. You should see your new shared mount at the bottom of the output. Donny at Ubuntu NF tables mount ... Donny at 192.168.0.10. cd into the remote directory and create some files. Verify that they actually do show up on the server. At the end console of a server VM, create some files in your own home directory. Verify that they show up in the remote directory of your client VM. You've reached the end of the lab. Congratulations. With this lab, I just showed you how to mount your own home directory from a remote server. You could also mount other server directories by specifying them in an SSHFS command. For example, let's say that I want to mount the Maggie files directory with the remote 3 directory as my local mount point. I choose that name because Maggie cat is sitting here in front of me where my keyword should be. Just do it like this: SSHFS Donny at 192.168.0.53 Maggie files home Donny remote 3. You can also make the remote directory automatically mount every time you boot your client machine by adding an entry to the etcfs tab file. But it's generally not a good idea. If the server isn't available when you boot the client machine, it could cause the boot process to hang up. Okay, so you've seen how to use SSHFS to create an encrypted version connection with a shared remote directory. Let's now log into the server from a Windows desktop machine, remotely connecting from Windows desktops. I know, all of us penguinists who would like to use Linux and nothing but Linux, but in an enterprise environment, things just don't always work that way. Yeah, you'll most likely have to administer your Linux servers from a Windows 10, 11 desktop machine that's sitting on your cubicle desk. In chapter 1, running Linux in a virtual environment, I show you how to use either Cygwin or the new Windows 10 11 shell to remotely connect to your Linux virtual machine. You can also use these techniques to connect to actual Linux servers. But some shops require that admins use a terminal program rather than a full-blown bash shell such as Cygwin. Normally, these shops will require that you use PuTTY on your Windows machine. PuTTY is a free program that you can download from here. Installation is simple. Just double-click to install the file and follow through the installer screens. Figure 7.2, the PuTTY setup wizard. You can open the PuTTY user manual from your Windows 10 11 start menu. Figure 7.3, the PuTTY user manual. Connecting to a remote Linux machine is easy. Just enter the machine's IP address and click on Open. Figure 7.4, creating the connection. Note that this also gives you the option to save your session, so if you have to administer multiple servers, you can open PuTTY and just click on the name of the server you want to connect to, and then click on Open. Figure 7.5, saving the session. As you can see, this is a lot handier than having to manually type in the SSH command every time you need to log into the server, and it prevents you from having to remember a whole list of IP addresses for multiple servers. But of course, you can't accomplish the same thing with either Segwin or Windows 10 shell by creating a login shell script for each Linux machine that you need to administer. Either way, you'll end up at a remote machine bash shell. Figure 7.6, logging into the PuTTY session. To set up key exchange authentication, use PuTTY-gem to create the key pair. The only slight catch is that you'll have to transfer the public key to the server by manually copying and pasting the key into the server's old authorized keys file. Figure 7.7, simply not key exchange. I've given you the basics about PuTTY. You can read about PuTTY manual to get the nitty-gritty details. Okay, I think that about wraps things up for our discussion of the Secure Shell suite. Summary. In this chapter, we've seen that a default configuration of Secure Shell isn't as secure as we'd like it to be. And we've seen that what to do about it. We've looked at how to set up key-based authentication and two-factor authentication, and we looked at lots of different options that can lock down the SSH server. We also looked at how to disable weak encryption algorithms and at how the new system-wide crypto policies on RHEL 8, CentOS 8 and RHEL 9 or Linux 9 make doing that really easy. Along the way, we looked at setting up access controls and at creating different configurations for different users, groups and hosts. After demoing how to confine FTP users to their own home directories, we use SSHFS to share a remote directory. We wrapped up this chapter by presenting a handy way to log into our Linux machine from a Windows desktop machine. Conspicuous by their absence are a couple of technologies that you may have seen recommended elsewhere. Pork knocking and fail to ban are two popular technologies that can help control access to an SSH server. However, they're only needed if you allow password-based authentication to your SSH server. If you set up key-based authentication, as I've shown you here, you won't need the added complexity of those other solutions. In the next chapter, we'll take an in-depth look at the subject of discretionary access control. I'll see you there. Questions. Which of the following statements is true? Secure Shell is completely secure in its default configuration. It's safe to allow the root user to use Secure Shell to log in across the internet. Secure Shell is insecure in its default configuration. The most secure way to use Secure Shell is to log in with a username and password. Which three of the following things would you do to conform with the best security practices for Secure Shell? Make sure that all users are using strong passwords to log in via Secure Shell. Have all users create a public-private key pair and transfer their public keys to the server to which they want to log in. Disable the ability to log in via username and password. Ensure that the root user is using a strong password. Disable the root user's ability to log in. Which one of the following lines in the SSHD config file will cause botnets to not scan your system for login vulnerabilities? Password authentication? No. Password authentication? Yes. Permit root login? Yes. Permit root login? No. How would you confine a user of SFTP to his or her own specified directory? Ensure that proper ownership and permissions are set on that user's directory. In the SSHD config file, disable that user's ability to log in via normal SSH and define a root directory for that user. Define the user's limitations with TCP wrappers. Use whole disk encryption on the server so that SFTP users would only be able to access their own directories. Which two of the following commands would you use to add your private SSH key to your session keyring? SSH copy ID, exec user bin SSH agent, exec user bin SSH agent shell, SSH agent shell, SSH add. Which of the following is not on the NIST list of recommended algorithms? RSA, ECDSA, ED25519. Which of the following is the correct directive for creating a custom configuration for Caitlin? User match Caitlin, match Caitlin, match account Caitlin, match user Caitlin. Which of the following crypto policies provides the strongest encryption on RHEL 8.9 type distros? Legacy, FIPS, default, future.
Which of the following standards defines NIST's current recommendations for encryption algorithms? FIPS 140/2, FIPS 140/3, CNSA Suite B. Further reading. How to set up SSH keys on the Min10 Buster. How to configure the OpenSSH server. Setting up password as SSH. OpenSSH best practice for Unix, Linux, and BSD. Different SSH configuration for different hosts. SSH query as Shodan. Mozilla OpenSSH Security Guide. Execute commands on a remote system over SSH. CNSA Suite and Quantum Cryptography. FIPS 140/3. System-wide cryptographic policies on Red Hat Enterprise Linux 8. How to log out inactive users in Linux. Configure host-specific SSH settings. How to use SSHFS to mount remote directories over SSH. Padding Oracle attacks. How to use an SSH config file. Using the SSH config file. Answers. 1C, 2 B C E, 3A, 4B, 5C F, 6F C, 7D, 8D, 9C.